Okay, let me quickly summarize what I have done. So the title of the talk is like what can we predict from the integrated dispersion data sets. Um, so what I did was first I created a training data set, then a testing data set. For the training data set, we have 441 unique designs, meaning that we change the heights and the width of these rings. Uh, for all the rings, the outer radius is equal to 23 micrometer. For the heights, the range goes from 620 nanometer to 720 nanometer at the steps of 5 nanometer. And for the width, 750 nanometer to 950 nanometer at the steps of 10 nanometer. So we calculated effective indices at 171 wavelength values from 750 nanometer to 1.6 micron. And what we did is actually we used four different Sellmeier equation models, set of coefficients. This comes from this paper of Dr. Srinivasan's group at NIST. So what they did is like they changed the gas ratio growth condition from 3 to 1 to 15 to 1, and then they fitted this permittivity profiles with these three coefficients for these four models. And for the test data, I wanted to have like 10% of the training data, like 441 was the training data length. So I just choose like 44. So let me, can I quit? And then for these randomly chosen integer values of width and height, again I did calculate the effective indices. Then from effective indices, I computed the integrated dispersion values. And the research questions are like, the first question is like, can we predict the ring width and the height from the integrated dispersion measurement? If yes, we can do that, then there are three other questions. The first one is like, which model is the best, or like, do we need a neural network to do this prediction? And then how many integrated dispersion measurements are required for a reliable width and height prediction? And then the third question was like, how does the noise affect these measurement precisions? And the last question is like, if we have the integrated dispersion data, then can we predict the right Sellmeier equation model? Like, is it equation model 1 or model 4, etc.? So I've been saying just measurements, but this is a purely numerical results study. So actually, these are all like numerical simulations. So like I should have used calculated instead of measured. So the first part, what we are going to do is like we will use some like neural network or some other machine learning model. So we will feed this network with our integrated dispersion data, and then we will try to predict width and height. So on the left, you see how the input values look like. So we have 171 values of wavelength, dispersion, integrated dispersion data. But of course, these are like normalized values. And on the right, you see the like training and testing data points. For the training, we have like a uniform grid. For the testing, we have some like random numbers chosen within the range. First, I use linear regression. I always do to see whether we really need something fancier or not. And as you can see, so on the x-axis we have the actual values. On the y-axis we have the predictions. So this is for the width, and this is for the height. And even though like we have the trends, the errors are serious. The mean value for the width prediction is like 8.8 nanometer. For the height prediction, 3.2 nanometer. And the maximum values of errors are really high, 38 nanometer and 15 nanometer. So that's why like simple methods like linear regression they are not good enough. So what I did is I used like here we have like a sequential neural network. I choose rel activation functions for the beginning. I also used some like built and tested some other neural networks. For example, ResNet gave really good results, but that's not the point here. So for this study, with this network, you can see the results are much better. Of course, here like there's no noise. But in this case, like the mean error for both width and height is less than 1 nanometer. So this is a really nice result. Of course, you can see that there are some outliers, like for example, this one and this one, like we have high errors. So we will look at those cases more closely. So I will call those cases like worst cases. And then we will also look at the main accuracy by looking at all the devices at once. Some notes, like for example, by using ResNet, we can definitely further lower these values. But ResNet, we have like more layers. It requires 3 or 4 times longer time for training. But for the following studies, we need something faster. That's why I just decided to go with this simple neural network. But there's one note here, like 171 was the length of the like x, right? And my general rule is like 2 to the power something, which comes right after this length. Like if it's 171, we should have 256 neurons in the first layer. If the length is like 15, we should use like 16 neurons in the first layer. Then we should decrease them gradually to have like stable solutions. The other thing is like, by the way, I put these notebooks on my GitHub repository. You could see them, the address in the first slide, like they are like ring dimension dataset, DS. But I forgot to fix the randomness. So every time you run these codes, you will get almost the same results, but with slightly different digits. So again, like don't surprise me if you get slightly different results. So here, like in this slide, I just show you the Sellmeier equation, Sellmeier model 1, but we have very similar results for the other 3 models, so I will not spend time on them. So then I added random noise of 50 megahertz, and results actually like didn't change much. Then I added 200 megahertz of random noise. Here we have a slightly worse prediction for the width, but better prediction for the height. And like you will see why adding noise. Actually, I will discuss briefly why adding noise sometimes help us. The second question was like how many integrated dispersion measurement are needed for reliable dimension. So what we are going to do is this time is instead of using the entire data set, we will use some part of it. And again, from this paper of Dr. Kartik's group, so here I saw that they took measurements at 3 different regions, one near the probe, one at much lower frequencies, slightly higher frequencies. So we will do the same thing. So we will use 3 groups of the integrated dispersion calculations, and what we will do is like we will eventually increase the number of samples in each group. Like first we will start with just 5 samples in 3 regions, then we will have like 10 samples in regions, and then we will look at the accuracy. And for every n number, we will have 20 trials. So to make this more like a Monte Carlo simulation, so basically in each group we will randomly choose n samples, so that we can have a better idea how our neural networks are performing. So let me explain one thing. Like I call these like average behavior and the worst behavior. So for the average behavior, like we will calculate the errors for all the devices for 20 trials, right? And then we will take the average of the minimum errors, maximum errors, and the mean errors. So this is for every single device. So that will be our average behavior. And the other group, is like I call it like worst case analysis. So what we will do is we will look at the devices which gives the highest error, and we will only take the average of, or like mean or maximum of those worst cases. For example, you see like the one at the very right or the second one from the left. Those are the somehow bad guys. So we will pay attention to those bad boys. Okay. So here the x-axis is the number of samples in each group, like from 5 to 10. As you can see, when n is equal to 5, we have very large errors, so that part is not very reliable. So for the no noise case, I will just pay attention to the cases with n is equal to 10 or higher in the following slide. So when n is equal to 10 or higher, you can see that the average behavior is like even for the highest error, um, you know, the highest error is around like 3 nanometer for the width prediction and 2 nanometer for the height prediction. Of course, when we use more samples, these errors go down. For example, if you have like 50 integrated dispersion measurements, um, of course, when there's no noise, we will have sub-nanometer precision. For the worst case, when we look at just one device which has the most like or least accurate results, you can see that, like for example, if we have like 30 samples in each integrated dispersion group, like we will have the maximum error of 17 nanometer for the width and around like 5 nanometer for the height prediction. But I have to mention that I generated this data set like by using 20 points per wavelength mesh quality. If we use a better mesh, let's say 40, 60, or like 100, of course it will take a longer time to compute, but the accuracy of these results will definitely go up, which we can do later. Then we look at the case where we have 50 megahertz random noise, and here like you can see that even with 5 samples in each group, the prediction errors are much less than the previous no noise case. So this is actually like not something surprising to the community of machine like neural artificial intelligence, because when we add random noise, actually we prevent overfitting. It is very similar to like regularization, right? We like as long as the noise is small, actually it helps our neural networks to learn better. So in this case, like when we have 10 measurements or so, the height width prediction has around like 3 nanometer error. The height prediction has less than 2 nanometer error for the average case. And for the worst case, again, like if we have 30 samples, 15 nanometer error for the width and like 5 nanometer error for the height prediction. Then we have like oh yeah, I just explained this. So then we have the results for the 200 megahertz noise case, actually pretty similar to what we had before, slightly higher errors, but again, compared to the no noise case, we don't have very different outputs. All right. The second, the last question was like, can we predict the Sellmeier model from the integrated dispersion data? And in this case, the input is same, like training this integrated dispersions, but the output is just like a category. And we have 4 categories, 1, 2, 3, 4. So this is a categorical, you know, categorization problem, not regression problem. And you see, like we use a softmax activation function in the last layer. So softmax activation function produces the probability of each group. So let's say that the outputs are like 0.9, 0.100. It means that it is 90% category 1. And when we look at the no noise case and when we use the entire data set, there is no error. We were able to classify all of them with 100% accuracy. Then 50 megahertz case, again, we were able to predict all of them. And 200 megahertz, the same thing. So if we have a very large integrated dispersion data measurement, this tells us that we can predict the Sellmeier model with extreme high accuracy. Then I did the same thing for the Sellmeier model prediction. So we changed the number of samples in 3 different groups from the spectrum. And what we see here is like if we have, for the no noise case, right, 30 measurements in each region or higher, we have 100% accuracy for the model prediction. For the 50 megahertz case, we need like 40 samples, and with the 200 megahertz noise case, we need something slightly more than 50 in each region. And here, like the red one is the mean behavior. Even like, for example, let's say, like 25 maybe samples, the misclassification error is like less than like, or around like 5%. So we will classify 95% of them accurately. All right, so yeah, that slide needs to be updated. Like in short, you know, we can predict the width and the height of rings, with sub 3 nanometer accuracy if we have large enough integrated dispersion measurements. For the Sellmeier model prediction, again, like 30 measurements in each group is really great. In that case, like we can predict, or like 40 samples, I'm sorry, we can predict with 100% accuracy. And there are so many other things we can do, but hopefully, this will summarize what I have done in the last month. Thank you for your attention. So let me find out how to finish this recording.